All right, first of all, we're going to estimate solutions of y to this diffy q using Euler's method. We'll start with the given point of 1, 2, and we'll get our next y value by using the previous y value plus the h value, which is zero point 0.1 in this problem, times the slope at the previous point. So for the point 1, 2, plugging them in, we get a slope of 7/4. So our next y value is the previous y value plus the h value times 7/4. All right, when we use the x value of 1.1 and the y value of 2.175, and we use this formula again, our slope is about 1.393. So using that, the next y value will be the previous one plus h times that slope. And doing this all the way down to 2.1 at a time, I use my calculator, and I end up with, when x is 2, we estimate that the solution for y will be about 3.032. All right, the next important part of this problem was doing the actual proof analytically. And so that looks like this. First, we do the separation of variables, and then we do the integral. And we can use the initial condition to find c when x is 1, y is 2. So c is negative 13. And now we're supposed to check what's the solution for y when x is 2, just like before. In our Euler's method, it was, 3.032. Okay, and here, if we let x equal 2, then this is 4 plus 24 minus 13. And when we solve this equation, I would do that graphically. And I'd graph y equals x cubed minus 4x. And I'd graph y equals 15 and see where they cross. And they cross at the value 3, when x is 3 in the graph, which for this problem is y equals 3. So Euler's method was pretty it's pretty close. 3.032 versus 3.